In this video, we're going to consider Lewis dot structures in which the multiple bonds could form between more than one combination of atoms and the so-called resonance structure. In this slide, we want to consider one of the allotropic forms of oxygen, elemental oxygen, which is ozone. Ozone is a molecular species comprised of 3 oxygen atoms. We know that the Lewis dot structure, or a possible Lewis dot structure for this, involves an oxygen atom which is bonded to 2 other terminal oxygen atoms, as shown here. In this particular case, there's a total of 18 valence electrons for the oxygens, but we are forced to have a double bond between the 2 oxygens on the left in order to satisfy the octet for the central atom. This provides a double bond on the left, but a single bond on the right. And the prediction from this structure would be that the distance between the 2 oxygens on the left would be shorter than the distance for the 2 oxygens on the right. And in fact, this is not what is observed. So we need to come up with a better description of the bonding than provided by this single Lewis dot structure. In order to account for the experimentally observed bond distances between the central atom and the 2 terminal atoms, we need to come up with a better description of the bonding. In order to do that, we need to consider a delocalization of this double bond so that it could go to both of the possible terminal oxygen atoms. And so this is a bonding situation that is fairly common and one that can be described by resonance structures. Resonance structures are a result of the fact that when you make a multiple bond to satisfy the octet, if there's more than one atom that could have been used to make that multiple bond, we have an equal probability of having both of the structures as shown here. So 50% of the time it has a double bond to the oxygen on the right and a single bond to the oxygen on the left, whereas the other 50% of the time it has the double bond on the left and a single bond on the right. So this is the so-called resonance description, and in this particular case it results in the sharing of electrons so that there is not a full-blown double bond and single bond, but partial multiple bond character between the atoms involved. So in this case, we would say that the bonds between the central atom and the terminal atoms are more like a bond and a half. As an additional example of a species that can undergo resonance, we're going to consider sulfate, which is a polyatomic anion. In this particular case, we're going to use our table to keep track of the electrons in this particular polyatomic ion. So there are 4 oxygens and 1 sulfur. Each of the oxygen atoms has 6 valence electrons. Likewise, sulfur has 6 valence electrons. So we have a total of 30 overall electrons from the sulfur and the oxygen, but we also have to account for the charge. Since this is a 2- ion, we're going to add 2 more electrons for a total of 32 valence electrons. At this stage, we're going to draw the skeleton structure. The sulfur is going to be the central atom, with each of the oxygens being terminal atoms. So we use up a total of 8 electrons at this point in drawing our skeleton structure. And so we have 24 electrons remaining. At this stage, we're going to distribute the remaining electrons first to the terminal oxygen atoms. And so in this case, we give 6 electrons to each of the terminal oxygen atoms, which then results in using up all of the remaining electrons. Since this is an ion, typically the convention is that we're going to place the formal Lewis dot structure in brackets and include charge. So this produces the Lewis dot structure that you see here. At this stage, we have a Lewis dot structure that produces a octet for all of the atoms involved. So we want to first consider the formal charges for all these atoms. And so in this case, for the terminal oxygen atoms, the formula would be 6 valence electrons minus half of the bonding electrons. There's a single bond, so that we would subtract away 1 electron from the bond. And there are 6 lone pairs on each of the oxygens, so this would result in a -1 charge for each of the oxygen atoms in this particular structure. That's not so bad in terms of oxygen being very electronegative compared to sulfur, but we then have to consider the situation for sulfur. Sulfur has 6 valence electrons, and there are a total of 4 bonds for a total of 8 electrons, half of those 8 electrons, and then there are no lone pairs, so this produces a formal charge for sulfur of 2+. Well, that is a situation where if we were to add up all these formal charges, we do get the net charge of this ion of 2-. So not so bad, but there is another possibility, and that is if we were to go ahead and form multiple bonds between the oxygens and the sulfur. In this particular situation, we show a possibility where there are double bonds between the sulfur and 2 of the oxygens. Now, this violates the octet for sulfur, but sulfur is indeed in the 3rd period, and 3rd period elements can violate the octet because of the presence of D subshells. And so this is something we'll need to consider. So if we go ahead and calculate our formal charge for the oxygens that have single bonds, just as above, we have a formal charge for those atoms of -1. In the case of the oxygens that have a double bond, in this case we come up with a formal charge of 0, and that's a good thing in terms of our rules for Lewis dot structures. And then finally, the effect of this Lewis dot structure on the sulfur is that it produces a formal charge of 0. This is a more desirable Lewis dot structure than the one shown above. Well, the problem then is that the Lewis dot structure that produces the lowest formal charge, as we have shown here, also has the possibility of having resonance structures where we are going to distribute the formal negative charge on the terminal oxygens over all of the atoms. So if we have an exchange or a resonance of the double bonds to some of the other oxygen atoms, we can come up with additional Lewis dot structures. In this case, there are 4 of them, and as a result, the formal charge resides on each of those terminal oxygens, and so is more evenly distributed throughout this molecule.